When we start to look at the Big Bang Theory in detail, or any theory for that matter, one of the first things that we want to ask are, what are the assumptions that go into that theory? There are very few theories that start completely from scratch. You really need somewhere to start. So what are the starting points that we're taking to be true? And for the Big Bang Theory, there are really two key points that we're going to talk about. The first one is referred to as the Cosmological Principle. Cosmological Principle. And this says two things. First, that on very large scales, the universe is homogeneous. And this is just a fancy science word for saying that every point in space looks the same. So every point, same. So for example, if I have a loaf of bread, then each point inside that loaf of bread is made up of the same thing. It has the same kind of structure to it. So we say that that bread would be homogeneous. Whereas if I had something like raisin bread, then it would not be homogeneous. At some points there would be raisins, and some points there would actually be bread. So it doesn't look the same at every point. So that would be non-homogeneous. And the other part of the cosmological principle is that the universe on large scales is isotropic, which is another fancy science word. This one meaning that there is no special direction. So no special direction. So if I had a room full of air and there was no breeze or anything going through it, then that air would be isotropic. There's no special direction. Whereas if I have if there's a breeze going through that room and the air is flowing in some direction, well, then there is a special direction to that system. So what the cosmological principle says is that on large scales, the universe is homogeneous and isotropic. Now, you may be saying, well, from my perspective here on Earth, neither of these look true. It doesn't look homogeneous. For example, on the ground, there's earth and solid material, and then there's air around me. Those don't look the same. In space, we have parts where there are stars and parts where there are not stars, so that doesn't look homogeneous at all. You might also say it doesn't look isotropic. Gravity is pulling downwards on me right now, so that has a special direction associated with it, and you can say that we're being pulled around the sun, so the Earth being pulled towards the sun, that's a special direction. So how do we justify that this cosmological principle is actually true? And the key point is that the cosmological principle says that the universe is homogeneous and isotropic on large scales. So to kind of demonstrate this point, I have two pictures of the Millenium Simulation, which is a computer simulation of clusters of galaxies and pretty much the large-scale structure of the universe. So in this picture, there's kind of a measure on here. This distance is approximately 100 million light years. And we see that each of these points of light kind of corresponds to a galaxy. So we see a large cluster of galaxies here and these kind of filament structures going off. And we see that this is clearly not homogeneous. So there's a cluster of galaxies here whereas there is a gap where there are very few galaxies over here. So this doesn't seem homogeneous. But if we zoom out to much larger scales, this distance here would be something like on the order of 500 million light years. So if we zoom out, then we can say, well, if I look at this box right here, we see kind of this structure of galaxies. And if I look over here, I see all these galaxies that look fairly similar to this. All of these different spaces, if I look on large enough scales, look pretty much the same. So this is what we mean by when we say we're homogeneous and isotropic on large scales. Now, this is a computer simulation, so you have to be a little bit careful what conclusions you draw from it. So we can actually look at the galaxies that are actually in the night sky. This is a picture of the Hubble Ultra Deep Field, and we see some kind of objects that stand out. These are galaxies that are in the foreground, but all of these tiny points of light out here are all individual galaxies that are very distant. So these background objects, these background points of light, take up a huge region of the sky, and we notice that if I look at a large enough area, then the scattering of background objects in this region of the sky looks pretty much the same as the scattering of background objects in this part, same as the background in this part. So we see that if we look on large enough scales, and the scale that we need to look at is something larger than 500 million light years, then we see that the cosmological principle seems to hold. So that's the first assumption that the Big Bang Theory makes. The second assumption is referred to as the universality of physical laws. Universality of physical laws, which is again a fancy science way of saying something very simple. Essentially, the idea that our laws of physics that we have studied and begun to understand, the laws of physics are the same at every point in the universe. At first, this has been just an assumption that was made, but more recently we've actually been able to test this by looking at very, very distant galaxies and bright sources of light from those galaxies and quasars and other distant objects like that. By seeing the reactions that are going on in these distant objects, we can kind of put limits on how much the laws of physics could be different in different regions of the galaxy, and there are reasonably tight limits that have been put on that. So it seems that all of the physical laws hold everywhere in the universe. And specifically, the physical law that is going to be most important for the studying of the Big Bang is general relativity. So I recommend that that if you're interested in this, you take a look at the playlist on general relativity, and that'll give a bit more of a description of this theory. But just to kind of overview what we're going to need for the understanding of Big Bang, is that general relativity is Einstein's theory of gravity. And the important thing about it is that general relativity doesn't describe gravity as a pulling force like Newton's law does. Rather, gravity is the result of the curvature of space-time. So what we have is that mass and energy can actually curve the space around them. So curve space. And this curved space will tell mass and energy how to move. So mass and energy curve space, the curved space tells mass and energy how to move. For instance, in our solar system, the sun, which is by far the largest mass in our solar system, curves the space-time around it. And this curved space-time is actually what tells masses like the Earth and the other planets how to orbit around the sun. And this is going to be a very important kind of concept to understand in terms of the Big Bang Theory, because when we talk about space expanding, so in the very early universe, we had this hot, dense state, and when we talk about the Big Bang, the image that often comes up is that all of the mass is compressed in this very small space, and then just out here is all empty. And that this mass somehow explodes into empty space. Now, this is not the case. What we have here is all of space and time, this curved space and time is actually curved up in this small space. And as the universe expands, it's not the mass and energy in the universe expanding into some larger space. The geometry of space itself is actually what's expanding. So this is expanding geometry. And we'll talk in the next video about what the geometry of the universe is like and what we really mean by expanding, so I'll go into more detail on this. But just for a start to understanding the Big Bang Theory, the two main assumptions that go into it are the cosmological principle, that on very large scales the universe is homogeneous and isotropic, which seems like a fairly reasonable assumption based on the observations that we see, and also the universality of physical laws, that all of our laws of physics are the same wherever we go in the universe.